sources of energy. Though there are some other sources like lipids, proteins, but of course the brain cells will make use of these carbohydrate sources. Now, carbohydrate is described as a polyhydroxyaldehyde. When we say poly, several. Hydroxy, you have OH. Hydroxy, hydroxide. Aldehyde, when you say aldehyde, you have this. You have C double bond O, you have then H and OH. That's the structure of aldehyde. So in other words, carbohydrates are made up of this, poly. Hydroxy with OH and this. Of course, this one, aldehydes. So that's the constituents of carbohydrates. Or, it could be polyhydroxyketone. So you have this structure, ketone, C double bond O, you have the R and R sub 1. R stands for our radicals. So any radicals would bind with this and the other one, so that is our ketone. So our carbohydrates are made up of that several structures of aldehydes and ketones. Of course, with the OH. That gives these compounds on hydrolysis. Now, when you say hydrolysis, hydro means water, lysis means splitting. So there's splitting of water. Okay? Now, carbohydrates, of course, as you mentioned, it's the energy source, the main energy source. So when there are other sources, like lipids and proteins, as long as there are carbohydrates, the cells will make use right away of carbohydrates as energy source. Now, carbohydrates can be classified as to monosaccharides, disaccharides, and polysaccharides. And we have the building blocks of carbohydrates. We have the monosaccharides. We have the word mono, means one, saccharide, sugar, meaning one sugar unit. And that's the simplest sugar, the building block. When you say building block, say in a concrete building, now when you try to strip it off, or say break it into its smallest pieces, I mean a functional unit, then you will end up having the hollow blocks. Are you with me? Say hollow blocks, say in a concrete building. So the hollow block serves as the monosaccharides. Okay? So it's a carbohydrate that cannot be hydrolyzed. You cannot break it into simplest form anymore because monosaccharide is already the simplest form of carbohydrate. So you cannot hydrolyze it or break it into simpler carbohydrate. So monosaccharide is the simplest unit of carbohydrate, the building block of carbohydrate. And it has its general formula. You have carbon, N, H, hydrogen, 2N, and then O, oxygen, which is N. So in other words, if we place number there, or number of atoms per carbon, say for example, you have carbon 6, then what is the, say if there are 6 atoms of carbon, so you have C6, what is then the total number of hydrogen atoms? 12. And then how about the oxygen? How many atoms? 6. So whatever is the number of carbon is the same with the number of oxygen. Then it would be doubled for hydrogen atoms. So that's the formula for carbohydrates. It's easy to remember. Okay. So of course the N there may vary from 3, meaning triose, to 8 octet. Octose, octet. Okay. Now we have some types of these monosaccharides, or say you have the aldose or mga aldoses and ketoses, ketose. Aldose are monosaccharides containing an aldehyde group. So monosaccharide can be an aldehyde or a ketone. When we say aldehyde, you have that structure, and or it could be ketoses or ketose, you have that structure ketone. C double bond O, then you have the two, say two pillars there, the R and the R sub 1. So the radicals, two radicals. Okay. Now there are different classifications of these monosaccharides, which are classified based on the number of carbon atoms. Okay, say it's easy to remember. Say when you are given the name triose from the word tri, meaning carbon atom is 3. So there are 3 atoms of carbon, triose. So when we know already the number of carbon atoms there, or the number of carbon atoms, then it's easy to place the number of atoms for oxygen and hydrogen. Say you have the word triose. The carbon is 3. And what is the hydrogen? So you have what? Times 2. So 6. How about oxygen? Okay, it's 3. So that is triose, trioses. Like for example, glyceraldehydes. Those are trioses. Then we have the tetrose, tetra. What's the meaning of tetra? You have 4. So meaning the number of carbon atom is 4. So when the carbon atom is 4, how about the oxygen? 4. How about the hydrogen? 8. Okay, 8. It's easy. When say in the quiz or in the exam, you're asked to give the formula of the following monosaccharides. It's easy. Like as if you're eating balut. Very, very easy. Tetrose, pentose, from the word penta. Okay, 5 carbon atoms. And for the hydrogen is 10. And oxygen is 5. It's easy. So without looking at the formula there, you can easily distinguish or you can identify. Hexose, hexa. Okay, from the word hexa means 6. 6 carbon atoms. So C6. How about hydrogen? 12. Oxygen 6. Hepta. So we have some example of hexoses. We have last. I'll be giving you several examples of hexoses. So 1, glucose. Glucose, fructose. Later, we mention all with their corresponding structures. And then you have the word heptose. Hepta. Hepta means? Okay, you have 7. Hexose 6, heptose 7, 7, 14. Okay, carbon is 7, hydrogen is 14, oxygen is 7. Octose, octa, 8. 8, 16, then 8. So it's easy. It's easy to remember. Now there are only 2 types of trioses. I mentioned a while ago, glyceraldehyde. So glyceraldehyde is a triose, the same with dihydroxyacetone. Now these 2 trioses are actually intermediate products when you break down glucose during glycolysis. We say lysis means splitting or breakdown of glyco, you have the word glucose. So during the breakdown of glucose, one of the intermediate products, or these 2 are the intermediate products. The trioses, glyceraldehyde and dihydroxyacetone. So what's the difference? Of course, you have there. So both are made up of carbon atoms. So you can see now the difference. For glyceraldehyde, you have carbon, hydrogen, oxygen, CHO. Up. Then on the 3rd carbon, so you have here the 1st carbon. That one is the 1st carbon, 2nd and 3rd Now for dihydroxyacetone, whatever is on top, CH2OH, the same with the third carbon, CH2OH, and then C double bond O. That's for your dihydroxyacetone. It's a ketose, and this one aldose. Oh. So when glucose or that monosaccharide is broken, it could give you an intermediate product, an aldose or a ketose, which is a triose. Okay? So, any question here? Okay. So, you have here the structure of these trioses that we mentioned a while ago. Oh. Now, when we say enantiomers are mirror image. Mirror image. Now, like this one is the mirror image of this. This is the enantiomer. This one is the mirror image of this structure. Okay, so when you look at yourself in the mirror, say if your mole is on the left, sa mirror, nasa right. That is enantiomer, mirror image. Okay? So you have the glyceraldehyde, the simplest aldose that contains a stereocenter and exists as a pair of enantiomer. This is known as the stereocenter. So you look at the stereocenter, there is now change. So this one is on the right, and the mirror image or the enantiomer of this glyceraldehyde is on the left. Okay? So this is stereocenter for that glyceraldehyde. Now, monosaccharides could have several projections. You can write its structures in several projections. Like you also, you can make, say when you take picture, you can have several projections. Pwede ka mag-side view, the side view projection, or the front view, or maybe the back view, or mga slant, sa pa na yung mga post. Okay? So, those are different projections. Now, the same is true with monosaccharides. Monosaccharides have several, you can write the structure in several projections. So, we say Fisher projection is a two-dimensional representation. Okay, for showing the configuration of tetrahedral stereocenters. So, this is an example of a Fisher projection. That one. Fisher projection. Now that is in honor of Emil Fisher in 1891. It was discovered in 1891. That these structures of carbohydrates can be written in this manner. So when carbohydrate structures are in a Fisher projection, so you can describe the carbohydrate as D or L. When we say D or L, okay, you look for the penultimate carbon. Now like this, we have the last carbon before the fifth or the sixth carbon, say for example, kani. So this is the first carbon, the second, third, fourth, fifth, and sixth. This is hexose. This is glucose. Where is now the penultimate carbon here? So this one. Penultimate carbon. So you have here the fifth carbon. Look at it here. Now, try to look at the location of the OH. Now, when the OH is found on the left, it's easy to remember. It's easy to remember that it is now described as the L-glucose. Are you with me? Okay. So, you have here the L-glucose. Now, how about this? If it is on the right, the other way around is the D-glucose. So, it's found on the right. Okay, so if the OH location is found on the right, In the penultimate carbon, then you have now described it as the D-glucose. Again, it's easy for the L, left. L stands for L, left. It's easy to remember. The other way is D. That is in the Fischer projection. Left, then the D, OH is on the right. So again, we count it. First, second, third, fourth, fifth, and sixth carbon. Okay? So, you look at the fifth carbon and as to the location of the OH. If it's found on the left, then it's described as the L. Monosaccharide. And on the left, on the right, it's the D, monosaccharide. Okay. Now we have this most common Petrosses, tetra. So I gave you a while ago examples of trioses. What are those trioses? The glyceraldehyde and dihydroxyacetone. So you have the aldose, triose, and the ketose, triose. Now this time we have another example, Petrosses. So meaning they are made up of 4 carbon atoms. Okay. So you have the first carbon, that one. So you have the first carbon, second, third, and fourth carbon. Now you cannot see the carbon written in here, but it is understood that it is bonded with carbon. Are you with me? Yeah. So you have the first carbon, second here, so this is carbon, and the third carbon, then you have the fourth carbon. So this is tetros, or tetra, 4 carbon atoms. Okay. Now try to look at the penultimate carbon. Say the location of the OH is on the right. That's why they are D. D erythros, D threose. So these are some Petrosses. Then we also have D ribose. So this is already pentose. Penta means made up of 5 carbon atoms. The common Petrosses are D erythros and the D threose. That's the 2 most common Petrosses. And we have the 2 most common pentoses. You have the D ribose and the 2-deoxy-D-ribose. So you count first carbon 1, first carbon, second, third, fourth, and fifth. Why it's D? Because the OH is on the right. The penultimate carbon's OH is on the right. Now, the D-ribose is a sugar found in the RNA, ribonucleic acid. Okay? RNA. Are you familiar with RNA? So, some of the genetic materials, like for example, it's a genetic material in tobacco mosaic virus. Some viruses, there are some viruses whose genetic material is RNA. And the sugar is made up of this D-ribose. Now, for us, we have the RNAs. Of course, when our genetic material, the DNA, is activated, then it produces several types of RNAs. Okay? So, the sugar is called ribose. It's very, very common in us, the ribose. Now, when we say 2-deoxyribose, now on the second carbon, the oxygen is removed. You have the word D, means removal. Oxy is oxygen. So, the oxygen on the second carbon is removed. That's why it's called 2-deoxy, then D-ribose. The rest are the same. So it's just a matter of removing one oxygen atom on the second carbon. Did you get it? That's why it's called 2-deoxy D-ribose. Ribose 1, 2, 3, 4, 5. Get it? Now, this 2-deoxy D-ribose is the sugar found in our genetic material, DNA. Deoxyribonucleic. See that one? That model. You project next model. That model that is our genetic material. Now, a portion of that is that portion that codes for a protein is called the gene. Okay? And that gene makes up a protein. And that makes up you and me. Okay? So you have here, so when you say 2-deoxy-D-ribose, there is just removal of one oxygen on the second carbon. D removal. So that's the sugar in the DNA, which is our genetic material. Now we also have these three most common hexoses. Hexa means 6 carbon atoms. 1, 2, 3, 4, 5, 6. Okay? So we have our glucose. 1, 2, 3, 4, 5, 6. Oh, the other one is galactose. Then the other one is fructose. 1, 2, 3, 4, 5, 6. So these are the three most common hexoses, okay, in the biological world. Okay, where you could find fructose, the monosaccharides in fruits, the sweetest sugar, in honey. It's the sweetest sugar. So that contains 6 carbon atoms. Why D? Because the penultimate carbon's OH is found on the right. Okay, so you have here. This is galactose. This is the sugar which is found in the milk. So lactose, galactose. Lactose is a disaccharide which consists of glucose and galactose, the milk sugar. So this is one of the constituents of our milk sugar. Okay. And then of course you have the glucose, which is also named as dextrose. So its other name is also called dextrose. So the word dextrose that contains actually glucose. That is the same with glucose. Okay? So when you have that IV intravenous, when you suffer, when you're sick, when you're given intravenous dextrose, you have glucose as the constituents. Okay? Any question here? Okay, now in your page 443 in your textbook. Now there are several examples there. It's tabulated. Kindly look at your textbook, page 443. Several, I think there are 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 examples of monosaccharides. Okay, what are they? We have allose, aldose, glucose, manos, glucose, idose, galactose, and stallose. Now, we have some tips. So it's easy for you to construct their different structures. Now, you have some tips here. But of course, these tips are only applicable to these examples. and the sequence of these examples of monosaccharides. Okay, like this. You have some tips. You have allose, altrose, glucose, mannose, glucose, idose, galactose, and thallose. Are you following?
Yes.
Okay. So we can place an abbreviation. And the acronym for that. An angel guides me going inside God's temple. An represents the A here, which is allose. Angel, A, another monosaccharide, altrose. And then you have G, guides, which represents glucose. And you have me here, the M, that represents, that corresponds Manos. Going, G, that corresponds glucose. Inside, I, idose. God's, G, galactose. Temple, T, thallose. Now, in writing the structure class for these monosaccharides, now, they only differ in this, okay, in this portion. The second, third, and fourth carbon. The rest, they are all the same. Are you with me? Okay. Say again. Say, the first carbon, all of these monosaccharides have this structure, CHO. This is the first carbon. All have CHO, so there's no problem. And the sixth carbon, all have CH2OH. Are you with me? Now, the penultimate carbon, since they are all D, there. So, ang OH is found on the right. So, pareho sila tanan. They are all the same. First carbon, the fifth carbon, and the sixth carbon. Now, they only differ on the second, third, and fourth carbon. But we have this guide. Okay. Now, here, how to be guided in placing the H and the OH as to whether on the left or on the right. Now, there's no problem with the first carbon as what I have said. All starts with CHO. Now, on the second carbon, now for the, so we have here, alternate. Say, right for the allose, left for the altrose, right for the glucose, left for the mannose, right for the glucose, left for the idose, right for the galactose, left for the thallose. Meaning, right, left, right, left, right, left, right, left. Sa second carbon. Are you following? Okay. So, it's easy to remember. So, there are 8 of these monosaccharides. But the placement of the OH or the location of the OH would be written in this manner. Right, left, right, left, right, left, right, left, right, left, right, left. Are you with me? So, simply memorize this. An angel guides me going inside God's temple, of which A stands for allose, altrose, glucose, mannose, glucose, idose, galactose, and thallose. Now, how about for the third? Third, the location of the OH is for allose right and altrose, glucose left and mannose, glucose and idose right, and galactose and thallose left. So, yeah, right, right, left, left, right, right, left, left, right, right, left, some, say, citric. Now say, let's say example, yeah? Say, you write the structure of Manos without looking at your copy there in the textbook. Manos. Manos. Just remember this, no? Without looking at your textbook. Be honest with yourself. So, all starts with the same first carbon, the 6th carbon, the 5th carbon. They just vary on the 2nd, 3rd, and the 4th carbon. Manos. Asa man na? 1, 2, 3, 4. 1, 2, 3, 4. So, mo ni ang Manos. Okay, anybody will... Dali ka. Just try. With amino. You have the amino NH2. That's the amino group NH2. So they're composed of the NH2 group in place instead of OH on the 2nd carbon. So look at here. Supposedly this is glucose. However, the OH on the 2nd carbon is removed and replaced by the amino group. So this is now red, so the same B, because the penultimate carbon's OH is found on the right. So you have here supposedly glucose, but OH is removed, instead replaced by the amino group. So it's now read as D-glucosamine. You have glucose and amine joined together. Are you with me? Okay. Glucosamine. Now, the rest, palihutanan with glucose, except for the amino group, the 2nd carbon. Okay? The same, Manos. The Manos. But what is replaced? The OH is now taken and is now replaced by amino group. So that's why it's named now as the Monosaccharide, meaning Manos and amino group. Okay. Then we have here galactose. Galactose, the OH is removed from the 2nd carbon and is now replaced by, you have the amino group. So these are the common amino sugars. Glucosamine, monosamine, galactosamine. Okay. Now we also have another, the N-acetyl-D-glucosamine. Now here, on the 2nd carbon, not only the amino group is added, but as well as the acetyl group. So we have here the acetic acid, or say the acetyl group. So you have here the acetyl group, which is bonded with the amino group. That's why it's called N-acetyl-D-glucosamine, meaning the acetyl group is bonded on the nitrogen. And this is now the acetyl group. And of course, you have the D-glucosamine amino, so which is the amino group is bonded together with the acetyl group. Or we term that also as the NAD, N-acetyl-glucosamine NAD. This is very, very abundant in nerve cells. These are some sugars, the amino sugars found in the nerve cells, especially in our brain cells. NAD. So these are the 3 amino sugars common in nature: glucosamine, monosamine, galactosamine. Okay, take note of this. Okay, now remember the aldehydes and the ketones. This one, aldehydes and ketones. These are constituents in the sugars. They may also react with alcohols. Now, when they react with alcohols, they form hemiacetals. When we say hemiacetals, we have this: COCOH. So, when ketone or aldehyde reacts with COCOH. Hemiacetal. Are you with me?
Yes.
So any ketone or any aldehydes react with alcohol that will form hemiacetals. COCOH or COCO. It's easy to remember, COCO. Now, the acetal, we say acetal group is COCO. COCOC. COCO. Acetal group. Okay. Okay. Now, so in question with the Fisher projection, we will come to this when we discuss later reducing and non-reducing sugar. What is the importance of this hemiacetal? This hemiacetal group. Now, in identifying whether the following sugars are described as reducing or non-reducing sugars. We'll come back to this hemiacetals. Now, on the other hand, we also have another projections for our sugars. So as what I have said, the structures of sugar or monosaccharides can be described as in a different projections. Fisher projection, or you have the Hayward projections. But it's Fisher projection, so you have to specify whether it's D or L. But in the Hayward projection, you have to specify the monosaccharide, or say the sugar, whether it's in the beta or in the alpha. Beta or alpha. Are you with me? So you have alpha glucose, beta glucose. Okay? Just like this. Say, that is in the Fisher projection. But when you write it in a Hayward projection, this is how it is written. So you have here the first carbon, the second carbon, that is the first carbon, the second carbon, third, fourth, fifth, and the sixth carbon. So that is in the Hayward projection for the hexose or glucose. First carbon is OH now. Second, third, fourth, fifth, and the sixth carbon. Of course, we have that lone pair of electrons of oxygen. Now, in Hayward projection, we have to describe the carbohydrate, whether it's alpha or beta. How? Now, say for example, we have here. Okay. Now, you can have it. Okay. Now, in the Hayward projection, we have this terminology of carbohydrate chemistry. The B or the beta means that the OH on the anomeric carbon, this is now the anomeric carbon, first carbon, is on the same side of the ring as to the terminal CH2OH. So this is the terminal CH2OH sa ibabaw. Ang anomeric sa first carbon. Now, if in the Hayward projection, if the location of the OH is the same, like this, the same, like this. So this is our terminal carbon. This is our anomeric carbon. If the location of the OH is the same on the terminal carbon, meaning nasa sa ibabaw, up, nasa sa up, then we will describe it as the beta. Beta monos, say beta monosaccharide. Okay? Okay, look at the OH, it's up. The terminal, say you have here, CH2OH, up. Now, on the other hand, kung ang OH is nasa ubos, if it's carbon. No? The CH2OH, na siya sa ubos. Ang kanina sa ibabaw. So, it is described as alpha. The rest, they're just the same. So, how to describe it, whether it's beta or alpha. So, ang anomeric carbon, so tanawin niyo ang anomeric carbon. If the OH of the anomeric carbon is down, that is alpha. If the OH of the anomeric carbon is up, then it's beta. Okay? So, beta, then alpha. Beta, alpha. Okay? Any question? So, it's like this, no? You have here the first carbon. So, you have the second carbon, H. Kung ang here, ang OH is on the right, ubos siya. Kung ang OH nasa left, ibabaw siya. First, second, third. Kung ang fourth, kung ang OH nasa left, ay sa right, ubos siya. Like on the second carbon, nasa sa ubos, kung nasa sa right. If you are on the right side, you have to be down. You have to be humble. It's easy. So, when you are on the right side, you have to be humble. So, sa ubos. Ubos ta. Okay? So, for us to remember. Say when you are asked to write the carbohydrate, say from Fisher to Hayward projection. So, if the OH is on the right, then in the Hayward projection, it's down. Okay? Alpha, first, is always down. Like Jesus, alpha and omega. Siya pwede sa ibaba. So, we have to be humble. Alpha, down. This is easy to remember. We have this spiritual implication. So, if on the left, you always have to be up. Up. So, H, up. Okay? So, first, second. Second is, first, second. Third is on the left, then up on OH. Okay? Any question? Pwede po siya, you can write it also or describe it as the beta-D-glucose. Beta-D-glucose. They're just the same with beta-D-glucopyranose. Because the structure is already a pyranose in the Hayward projection. But this can also be written as beta because the OH is up. So D-glucose. This one, alpha D-glucose. So if you are asked from the Fisher projection, you write it in a Hayward projection. And then describe it whether it's alpha or beta. So if you are asked to write the alpha D-glucose, alpha down on the anomeric carbon. OH is down, alpha. And then, there, right, the second OH is down. The third carbon on the left, then up. Then, the fourth carbon on the right, then down. So when you are right, then you have to be down. It's easy, right? Okay. When you are right, so meaning when that OH is on the right, then it has to be down. So that represents you and me. Okay. The OH there. Okay. So of course you have this, all have this, says the OH, then H here. Okay? Any question?